it's a lot of, oh, did we not record? Sorry. That's cool. All right. Would you like me to start again?
No, you're all good.
Okay, cool. All right. We're at the start still anyway. But this is the why it's relevant to you, and any terminology that you might come across and you might need to just refresh on, like, what does it mean? I'll try and actually say the full word where I can. But continuing on. So database categories. Now there's so many different ways which we can organize databases, and there's different categories, but I found like the four most common and clean ways to do that and to explain it to you would be these four categories. Now, we're not going to look at all of them. I'm just going to focus on this one with the red circle, relational databases, because that's the most relevant to you right now. But you will see, and we will touch on very briefly, non-relational. I think it's important because you need to know, I guess, what the difference between those are. If you understand this one, you understand, oh, that's what that one's about. But essentially, relational databases store structured data in tables, and that is not the case with non-relational. So it's semi-structured and unstructured data that is catered for in non-relational databases. It's stored in different ways, and it depends on what type. There's types within these as well, so it gets very, very overwhelming, but I think this is a good breakdown. So you've got hierarchical, which is kind of like a tree, and this is very fast when you use this. You actually, Windows registry is a very good example of this. You can pull up something really quickly. And it's fast because there's very finite paths to get to the information, but it is very rigid. So the trade-off is the speed. And object-oriented deals with data as complete objects, like we've kind of been looking at in OOP. And the information comes all at once, like in a package instead of multiple tables. So I've just listed some examples of some of the databases that you've probably heard of or seen. Maybe you're looking for a job right now and you see some job ads mention these. It's a great thing to actually know what is that? What type of data are they using for this application, etc. So the history of databases dates back long before computers were invented. So in the past, data was stored, in journals, filing cabinets, very inefficient, taking up space, all of that. And it still kind of is sometimes, which is not good, but we're getting better. But once computers came along, it kind of changed for the better. So we started having computerized databases, and this guy called Charles Backman, that's not him, by the way, that's another guy. I'll talk about him in a sec. But Charles Backman, he designed the first database, and that was called an integrated data store. And then that was followed on by IBM's information management system. And these databases were very cumbersome to use. Like, they weren't very intuitive, and you had to go through and manually find what you wanted, which kind of defeats the purpose nowadays when you think of it, how far we've come. So these were the two main models. But then it came relational databases. So this person here, this guy is Edgar Codd. He introduced this model and was like, hey, why don't we just be more organized, store everything in discrete tables, and make links between them when we need to. And everyone was like, yes, why haven't we thought of this before? So this, around the time that this happened, was also around the time that SQL, which is the language used to manipulate data, started coming into the picture. And then after that was the dot-com bubble, and more mainstream use of data, and people started to care about how they were storing this. It's important. And now everyone really, really cares about it. But that's a little bit of a history. So relational databases predate any other type. And these are very well established. These came later. The other ones came later just to cater to specific circumstances where you have like weird unstructured data, that it's not so simple to organize. So because we're talking about relational databases mainly, I need to make sure that the terminology is there. So in a relational database, you model collections of entities. So in your notes, the Django notes, entities, and I might use entities and objects interchangeably in this talk, but entities are anything in the real world that you need to include in your application. So it can be a user, it can be a product, anything really. So each entity has its own separate table, and within the tables, you'll have columns. So these columns are known as fields or attributes, and these are the characteristics of the thing, your entity, your object, basically. So your objects, whatever it is that you're going to be making. So this is a student table, and the student names are housed in this column, their ages, and the course that they're studying. So the rows, 1, 2, 3, and 4. So the rows, they can be called records. You might see them, some people refer to them as tuples. You haven't done tuples, but don't worry too much. It's hardly ever referred to as tuples. It's more records that you'll hear. So these represent a single unique instance of an object entity. So remember how we were talking about making objects in OOP and how you can create things from classes? Yes, so one row is one unique instance object, linking back to what we did in the previous weeks. So in the next, yep, here we go. So structured data. So relational tables are a format for structured data, and each row has the same columns. So if you go across a row, they've all got the same columns and it stores the same type of information. So sometimes you don't need to have a value in a column, and you can actually specify this when you're creating or designing a database. You can say, hey, I don't think that we should make everyone put in, if there's a middle name column, for example, not everyone has a middle name. We shouldn't force everyone to put in a fake middle name just because we want something in that box. It's just an example. But we can do this by specifying that it can be null or empty. And each column stores data of a specific data type. So you've got here address, that would be a string, for example. Price, this might be float, maybe. I haven't actually, it could be whatever you want as long as it actually makes sense for the data, but I haven't actually annotated that. But that would be good for future, actually. I'll put that down. You can have a date as a data type, and obviously integers for your IDs. So lots and lots of different ways to store the data depending on what you need. And there's certain nuances with the data types depending on which database you use. Some of them have many more, or like different versions of the same. All you need to know is they can store whatever you need, essentially. You just have to tell it what when you're designing a database. And another element, so we've done the tables. So another key thing about relational databases that you need to know about, and they're very important, is primary keys. So each table in a relational database must have a primary key column. So this column, there's rules to this column. This column uniquely identifies a record from any other record in the column, and the rules for which column to make your primary key are written down here. So a primary key must be unique and identify with only one other record in the one record, sorry, in the table. It needs to be never changing. So you can't have, for example, someone's address be a primary key because they might change their address in the future. And when you go and look for someone based on their address, you'll run into problems. And primary keys cannot be null. So the values cannot be left blank. And that makes sense because if you're using that as your identifier for that instance or that object, that unique object, you need to actually have a value. So, okay. Yeah, so relational databases, third key component are foreign keys that you need to know about. So foreign keys, these are exactly what the name sounds like. They're keys in another table. They're foreign in another table. So what do I mean? It's a field in one table that references the primary key of another table. Okay, so we use these to establish relationships between tables and make sure that the data that we're entering, the values are consistent. So over here in this example, I've got a customer ID column, and this customer ID column is actually referencing the ID column in the customers table. So this is the primary key for this table, and we're using it in the orders table. And we need to make sure that that is an established relationship to make sure that anytime we refer to a customer, they actually exist. And I'll get to what that means or how that looks like in just a moment. Some rules for foreign keys. They can be null, so there can be blank. I mean, it would be great if it wasn't for certain things, but depends. And you can have more than one foreign key in a table as well, so there's not really any limits. So when we're talking about the benefits of foreign keys and primary keys, one of the things I mentioned, not by name, but just description, was data integrity. So they're crucial, both of these things, both keys are crucial for maintaining data integrity in the database, and they ensure that each row in the table has a unique identifier, like we mentioned, preventing duplicate data from being inserted. So on the other hand, so foreign keys, they establish relationships between the tables, and they ensure that the values in the column correspond to valid values, that is, in the primary key of another table. So when we enforce these constraints, the primary and the foreign keys help us to prevent data inconsistencies, and overall they improve the quality of the data that we're storing. So in this example, we have customers. So yes, customer was C3. Yes, customer. So customers primary key, C1, C2, and we're saying this C3, this is C3, sorry, is a customer, but we're trying to insert it into the table without a foreign key. Without a foreign key, this will actually be added to the table, even though C3 doesn't exist in the customer table at all. So there's only C1 and C2. But if we do have a foreign key, then it will not allow us to insert this row, all of this information about this, into this table. So it will say, hang on a second, C3 doesn't exist in this table. You can't add this information to this other table. That's what that does. So the way that we prevent data duplication and maintain data quality, that's what foreign keys do. So when we try, when we try and insert data in this way, you can get a lot of error messages and it can be a bit much, but if you've got it set up in the right way, you're much better off for it. So the other benefit is data consistency. So I did mention that, but didn't actually put a name to it. So it helps ensure the consistency. So when a foreign key is defined on a table, it establishes a relationship between the tables like we've seen. And it helps to ensure that the data in both tables remains consistent. So there's no point in you having two different versions of customer 3. That'll be really weird and confusing for everyone. So if we update the customer ID value in the customers table, the corresponding values in the orders table will also be updated. So I wanted to get to this part. This is the part, the query performance. So the third and really, really important benefit of keys, foreign keys and primary keys, is query performance. So when a primary key is defined in a table, the database engine can use it, I'd say, as an index. So this means that the data in the table is physically stored in the order of the primary key, and that can improve query performance. So when you want to retrieve data from the database, it doesn't have to messily scan through all of the rows. Everything's in order, and you can just pick out the one that you're looking for quite easily. And similarly, foreign keys also help in that process as well. So both of those make query performance efficient. I don't know if you've ever been using a website and it's like so slow, you're just waiting for information to load. You don't want that. You want to have fast performance. And this is just a GIF I found to show foreign key constraint. So the constraint here is that it won't let information be added, like I was mentioning before, to a particular table unless it exists in the other tables that you have the foreign keys on. So here we have user table, orders, and books, and you can't make an order unless you're actually doing it with a proper user ID, an actual user ID in the users table, and it won't let you put an order in if the product number, the book product number, is in there either. So it's a bit fast, but that's what that's showing you. So it violates the foreign key constraint and it won't let you add that information to the orders table because that's all in place. And just a quick note on SQL. So it's relevant and I think it's worth mentioning because we're dealing with databases and the language, the way that we manipulate data is through SQL. So that stands for structured query language. So we manipulate and manage our data with this language and we use statements to do that. And there's different types of statements or commands. I've actually just got a little diagram here outlining those different types of statements that you can use. The DML is more statements to do or commands with data manipulation. DDL is data definition, so defining data. DCL is data control, and TCL is transaction control language. You don't really need to know that. It's just good if you see or hear anything about that. That's what that is. But what you will see, or you might be curious about, is the different types of SQL that are used to manipulate data. You'll see there's different variations, and you might even learn one if you have an application that you're not using something like Django to develop in the future. So Transact SQL, I think Postgres, yes, Postgres SQL, and this one is procedural language SQL. So I won't go too much into that, and I'm just going to leave that there, and I'll probably share these slides later if anyone wants or knows a little bit more, wants to know a little bit more about SQL and the order of execution of these commands. It's pretty interesting, but that's just there as an extra. Just thought I'd quickly mention it. But this is the slide that I would like to focus on to wrap up this section on the components of relational databases. We've gone through most of this and we've talked about all the things that are great that happen when we use primary keys and foreign keys. Without them, this is what will happen. We'll end up with duplicate data, inconsistent data, and slow performance with our database. So we do not want that. And just a quick note on NoSQL databases. So the relational databases you'll hear often being referred to as SQL databases, and you also hear NoSQL as well. And this is something that really kind of confused me when I entered this world. I was like, right, SQL, NoSQL, relational, non-relational, oh, so many words. But non-relational databases can fall under the umbrella term of NoSQL databases. And I guess one thing to note is that when we organize data in actual predefined tables with predefined data types and all of that, that's what makes data structured. And we say that those databases have a fixed schema because they can't process anything else outside of that. So they can't process unstructured data. And SQL is used to manipulate the data in those databases. But with NoSQL, it's a different sort of way of structuring and, well, actually not structuring, of storing the data that's unstructured. So it's a database management system approach It's used to ingest, to store, retrieve unstructured data and semi-structured within a database. So we can't use SQL, and actually depends on the type of database specifically that you go for and use, because there's ways that you can use SQL-like languages on some databases, but generally speaking, that's why they're called NoSQL. You can't query them in the same way because the data is unstructured. And when I say unstructured data, it just means, like I mentioned, not having predefined data models or tables, and things like just, social media posts. If you have a social media post, that's going to change. People update social media posts. If you have a picture, you apply a filter, that changes that actual data quite rapidly. So with unstructured data, it can change very rapidly, but with structured data, things like bank statements, they're more, I guess, they have a lower rate of change. And just some examples of unstructured data would be the pictures, audio files, videos, maps even. But the flexible schema of NoSQL, which means not having that rigid table definitions and all of that, it enables the databases to ingest, the NoSQL databases to ingest unstructured data in their native format. So this, whether that's a text file, whether that's JPEG, MP3, and this isn't possible with SQL databases because, of the rigid requirements. So when the data is stored, so the flexible data models make it so that the unstructured data can have different data structures and still be stored within the same collection. And there's 4 different types, and I'm not going to go into them too much, but you will see them eventually in the future. There's key value, which is, seen before in terms of dictionaries with Python, column family, there's document, and then there's graph. But that's all I'll say on that. That's just a quick note. Now, representing databases before you make them. So there's a lot of moving parts when it comes to databases, and we need engineers, software engineers, when I say we, it's you, me, professionals, we need a clean visual way to understand how all the information works together and is related. So we don't want to be showing all of the data in our tables like we were just seeing before. Like, we don't need to see all of the values. We just want to see what the rules are and how it's all structured. So once you've worked out what your entities in your application are going to be, you've done all that hard work, you can create what we call an entity relationship diagram. And this helps to ensure that there are no flaws in your design before you continue actually coding and developing your application. So there's a couple of, oh, actually, I'll go back. Oh, I didn't talk about this. This is important. Sorry about that. So there's a couple of main parts you'll see to ERDs when you make these diagrams, and they have been covered very briefly in your notes, but I'll go through some of these. So the actual entities themselves are the tables, discrete tables. You've got your attributes. So these are the columns that we mentioned, and the data types will be defined as well. And the new thing here is cardinality. So these are the links between the actual tables themselves. So I'm going to go into that in more detail here. So lines of cardinality. So cardinality just refers to the maximum number of times an instance in one entity can relate to an instance of another entity. So remember that these are all one record, I should say. One record is one particular unique instance object of a customer, each with its own first name, last name, etc., etc. Same with an order. Everything is unique. Every row is unique and represents an object. So we're trying to, with these lines of cardinality, we're trying to describe how one entity can relate to the instances of, or the instances of one entity can relate to the instances of another entity. So some common cardinalities that you'll see are one-to-one. They describe how an instance of an entity can only be related to one instance of another. That might be the case in your application for two entities of different tables, or one-to-many. You might have an instance of an entity that can relate to multiple instances of an entity, and you can have many-to-many. So that type of relationship is where multiple instances of one entity can be related to multiple instances of another entity. Now, this one is really hard to deal with, many-to-many, and you'll hear a lot that you should avoid having many-to-many relationships in your application. There is ways around it. If you can't avoid it, you break down and have more tables basically, but it's a bit too much to go into for this, I think. But they're called bridge tables if you want to have a look at that later. They're the solution to complex many-to-many relationships. And you can get very detailed in how you describe the relationships between instances of separate entities. We use many different notations. I'm going to talk about one only, and that one's called the crow's foot notation. I find that this one's quite, it's nice. It's quite good to start with. It doesn't clutter up your ERD because all the information is already on the actual connection, the actual line. Basically, it's a notation to describe these sorts of happenings between instances of different entities. So I'm going to, I think I have I don't know if I had an example. I'll go back to this one. I thought I had a different example, but we can use this one. So here, how do you know how your orders and your customers relate to one another? How do you know what the cardinality is between them? How do you come to that point? So you would say, pick one table. You would say, okay, customers. Customers can have how many orders? Is there a limit to the number of orders that a customer can make on an application? You would hope not, because the person that wants to make some money is going to want people to keep buying more things. So that doesn't make sense. So they should be able to have one customer should be able to have many orders. Do you actually need to have customers make orders? Are you going to make all your customers on your website? Are they going to have to make an order? That's also sounds a bit ridiculous. So no. So we say with this notation, I don't know if you can see very clearly, but it's like a circle and 3 prongs coming out of it. The circle means 0, and the many prongs, the 3 prongs, means many. So we say that a customer can have 0 or many orders, and we put that over here next to the orders table. Then we do the same, but in the reverse. We say, okay, the orders. How many customers belong to an order, any one order? You would say 1, right? Because if you had multiple customers having the same order, the same exact order, that would cause a lot of issues, especially when you're shipping things and customers have different addresses and all of that sort of thing. You only should allow 1 customer per order. So that's why we say an order has 1 and only 1 customer. So that notation, that notation, going too fast. That notation is here, 1 and only 1. And the other one that we used was 0 or many. So you do that for every table, and you see how it relates to the other surrounding tables with that process. If you have one particular order, how does it relate to one particular product? So with the product, okay, with a product and an order, for example, does a product have to be part of an order? I mean, you can have things, if you've got like an e-commerce website, you don't have to have people buying it. It could just be there. Maybe no one wants to buy it. Hopefully that's not the case, but you don't have to have a product being part of an order. So that's why the 0, that circle is there. And the other side, the other part of it, the many part comes into it because you can have a product, one unique product being part of many orders. So maybe more customers will want the same product, and it can be sitting in someone's shopping cart and be part of different purchases, different customer purchases at any given moment. That should be allowed. So there should not be a limit. And that's why we say, so the products has 0 or many orders. And we depict it with, similarly to here, the 0 and the 3 prongs. It kind of takes some practice to get this down pat, this process, and this is sometimes good to have a sanity check with someone to make sure that you're determining these relationships properly before you start coding. So that is how you determine lines of cardinality in ERDs. And that's probably as hard as it would get, really. And it does get a little bit cumbersome, so you have to do that for every single table. Now we come to the exciting bit. So, okay, why do we care about that, all of that, for what we're doing? So Django is what you'll be using to make your full stack application. You're starting off with the back end first, and it's important to note that Django is an ORM tool. ORM stands for Object Relational Mapping, and ORM tools are designed to help people like you, developers, coding in OOP languages, like you, because you're using this, Django is Python, to interact with your application's relational database. So all the stuff that I've just talked about, designing a database, all of that, you won't need to do. I mean, you will need to actually have a plan for your database, but you won't need to query your database. You won't need to be able to write SQL queries, really is what I should be saying. You won't have to write SQL queries in order to access the information for your application. That's what ORMs do for you. They make that process easier. So just as an example, this is a SQL query. This is what grabbing the ID, the name, email, country, phone number of a particular user with an ID of 20 looks like. With Django, you don't have to write these. You use methods in Django to get the information. So this is getting the same information. And look how much shorter that is, which is really great for you. You won't have to worry about this side of things. So the way that this happens is this kind of like object-oriented layer in between, if you will. It does all that hard work for you, and it's inbuilt into Django, and you don't have to install anything or do anything, but it converts the Python code, Python objects, into, depending on what you're doing, it can convert it into particular SQL statements relating to those objects and vice versa. So if you're retrieving or you're updating, whatever it is that you're doing, that's what's going to help you actually do it without writing SQL queries. So how does this actually happen? So how does Django work and does all this magic? Because it is pretty cool when you look at how it does it. Well, we define in Django, we define model classes. So remember when we talked about classes a couple of weeks ago? Classes are that magic word in Python to create objects. You can create your blueprints to make more objects. So we use model classes. So the model is the single source of information about a particular entity in your application. So here, this is just an example, but you've got students, and all the things related to the students are going to be in that model for the student. And it actually kind of mirrors what you've been doing with classes. Like you've got the attributes. It is that, essentially. The model is that because it's a class. It's a model class. So the properties and the behaviors of the data you're storing will be defined within these model classes. And every single row in a table, you won't be able to see it unless you do a couple of things. But when you create your models and you actually create unique objects or instances, you're going to be populating data into your database. You just won't be able to see it happening. But every single row in the table is uniquely identified by its primary key, like we talked about, and represents an individual object instance of that class. So here we've got one student, one particular student, and their name wouldn't be data flare. That's just silly, but you get my point. So when we have these model classes, each one maps to a single database table. And you can read more about how, in more detail in the Django docs. It's quite extensive, but basically that's how it happens. So the Django maps an object instance and its attributes to the respective table fields. So these are the fields in your table. This is a product, for example, product table. That's been made because you've actually defined a product class and you say, hi, my product has a product number, it has a name, it has all these features, and it actually maps together the instances and the attributes of each instance to the table, all without you having to do very much, which is really cool. Now, we're getting towards the end, and I just wanted to point out some useful tools when you start your project. So if you're thinking about your application, you know what your entities are, and you want to diagram all of your entities, and you want to make an ERD or even a UML before that. That's what I do. I actually make a UML diagram before that, which I went through with the Perth cohort, but it's not really, you don't need to do that. You can start with an ERD if you've got a simple application. There's heaps of online platforms that you can use to do that, to make that process easier to have an ERD. So I've listed some here. Some of them might not be free. I think Figma has a free tier, but you have to pay for more functionality. I think most of them might be like that, but Draw.io is actually quite good. And as far as I know, I think that one is free. If you wanted to actually look at the database that you're creating with your application, you can do that. You can download SQLite. So it's a software library and it's serverless, self-contained. It doesn't take much to just get running, and you give it the file for your database from your application on your actual machine, and it gives you the representation, the database representation of all that data. So that's really good if you want to see in detail what you're doing, and every time you change something, what is happening at the database level. You also have some tools in VS Code that you could use. So there's some extensions. Draw.io is an integration tool, and you can actually visualize your ERD there. This might be good for when you're submitting. I know some of us in my cohort had, I think, PDF files attached for our ERD, but you can actually have this integration and see your ERD not as a PDF, but through this. And you can also use SQLite Viewer. That's another extension. If you don't want to download this and that's a bit too much, you can download this extension and it just shows you the database. You won't be able to do anything to it, but you can just visualize in VS Code your database, and every time you make a change, what's happened. It will help you understand what you're doing as well. And that's pretty much it, I think. Oh, yes, I found this really cool cheat sheet on relational database design. I don't know if people want to look at this, so I put it in here. It's quite detailed, so you might not be able to see it all. But there is some information in there that I haven't really talked about, and you can just ignore for now. It's not really relevant for what you need to do. So like join types, But all this stuff is because it helps you understand what you're doing, and every time you use Django, what's happening in the back and the magic of it. And I think I've got, yeah, Python WA. So we have a Python WA happening again in September, and there is a talk on testing. And I know that a lot of people were talking about testing and how do you write tests and all of that when we were doing Python. So I thought I'd quickly put that reminder slide in. And that's on the, I think yeah, so it's the 3rd of September, I think, but it's the first Thursday of every month. And we have reached the end. How did I do for time? Excellent.
Yes, Alicia, you smashed it on time.
45 minutes.
I know we've still got a little bit of time. If anyone's got any questions from what Alicia went through.
I should actually find the the window where the questions are. I've kind of just lost it. Give me 2 seconds. I think I just moved it.
The chat's pretty quiet.
Is it?
But feel free to jump off mute if there's anything that you want to ask Alicia.
Yeah. I'm happy to answer any question, even like more towards, your assignment and anything specifically geared toward the tools that I mentioned. Doesn't have to be about the content specifically. We've also got Bridget, who is my boss, actually. So she is very knowledgeable as well on databases. So if you do have a burning question between the two of us, I'm sure we could take care of it. No questions?
Clearly, you just answered everything so wonderfully that there's just no holes left.
I hope not, but there might be later. And I will endeavor to get these slides to Kate so that Kate can maybe share them for people that want.
Yeah, totally.
There's so many links that I used, so that's all there if you want to have a read of certain things that I used to make these slides. But yeah, that's pretty much it, guys. Thank you so much for joining me. And I hope that after this, you would be a bit more knowledgeable on how Django is working and doing all those things so that you don't have to go full, designing a database. It's just doing it for you, almost. Making it for you, I should say.
Love that. Another little reminder before we jump off the call today, that we do have our next webinar is on the 19th of September, which is Alexander Karan is hosting a webinar on API specs and how to get started, what an API is and all of that fun stuff. So that will be same time, 5:15 Perth time, 7:15 Brisbane time on the 19th of September if you want to join us again for that one.
Oh, awesome.
I'm going to pause the recording, but I think Alicia and I and maybe Bridget might hang out for another couple of minutes if anyone does have any other questions. But thank you, Alicia. We can give her a little round of applause, and I can see some thank you coming in the chat too.
Oh yeah, I just got the